Dr. Scott Stevens here with the second of our probability videos, this one on joint and conditional probability. Last time we talked about three different ways that we could assign probabilities, numbers, to events, things that could happen. The classical probability technique only works when every possible outcome is equally likely, but when it is, it works very well. You count up the number of different ways that the thing that you're looking for could happen. You divide that by the total number of ways that things could turn out in general. That fraction tells you the fraction of the time the event occurs, its probability. Subjective probability is basically an educated guess, and the quality of that depends on the quality of the guesser. We try to avoid them when we can, but sometimes we can't. In the business environment, the most common kind of probability is empirical. That is, the probabilities are estimated by looking at historical data and using the relative frequency of an event. What fraction of the time did it occur in historical data? It also has its limitations, but it's often the best that we can do. Today our goal is to take these individual probabilities, however we compute them, and to use them to find the probability that more complicated events occur, compound events. In particular, we'll be talking about two kinds of compound events, joint probability and conditional probability. Let's play around with these ideas a little bit. They're not too hard. We'll use classical probability on the 8 people that I have shown here. If I pick a person at random, how likely is it that person's a woman? Well, clearly, there are 4 people in my 8 pictures who are women, and therefore the chance of picking a woman would be 4 out of 8, or 1/2. Easy peasy. You try one. I'm going to pick a person at random from these 8 people. How likely is it that person will be wearing glasses? I'm sure you got it. These 2 people are wearing glasses, so it's 2 out of 8, which is 1/4. Okay, let's kick it up a notch. Let's combine these into the idea of joint probability. No, not that kind of joint. This is joint like in joint checking account. It means 2 things together, an and of the things. If I give a list of events, how likely is it they all happen? So the quick question I want to ask is how likely is it I'll pick somebody who's a woman and who wears glasses? Well, if you answer that question in the same way that you've answered the other ones, you won't find that you're doing a lot more work. Looking over all the pictures, it's easy to see there's only one person who is a woman and wears glasses. So the chance of getting a woman and glasses is just 1/8. But the question I'm interested in is, can I connect the answer for glasses and for woman to the answer of woman and glasses? And in this particular case, it's pretty simple. A woman has a 50% chance of coming up. Glasses have a 25% chance of coming up, 1 in 4. And the chance of woman and glasses ends up just being the product, the multiplication of these two. 1/2 times 1/4 is 1/8. And that was the chance of finding both a woman and glasses. Well, that was sweet. Does it always work that well? Well, let's try again and find out. This time I'm going to go for the probability that the person I choose is a man wearing a hat. But I'm going to do it in 2 stages. How likely is it you wear a hat? How likely is it you're a man? And then see if I can stick them together with multiplication to get man wearing a hat. Let's go. Pretty easy to figure out the probability of wearing a hat. All the people in the second row and the middle guy in the bottom row have hats. That's 4 out of 8, or 1/2. I want man and hat. So I'm going to put that together with probability of man. In probability, the word and will always imply times, but you do have to be careful. In our example here, the probability of wearing a hat was 1/2. The probability of being a man is also 1/2. If you try to do what I just told you, multiply those together, you get an answer of 1/4. But that's wrong. Out of the 8 people, 3 of them are men wearing hats. The chance of getting a man wearing a hat is 3/8. So it's not quite as simple as just multiply the probabilities for each individual thing to get the and of all of them. But if we think about things a little differently, we can figure out something that does always work. For that purpose, I'm going to imagine you here in an obstacle course, and you're required to clear the 2 obstacles of hat and man to end up with a man with a hat. Well, the first obstacle is the hat obstacle, and you know that to do that, there's a 50% chance that you'll succeed because the probability of hat is 50%. Now you might think that the man obstacle has a 50% chance too, but we know something about you that we didn't know about you before. We know that you cleared the hat obstacle. So If I want to figure out how likely it is you'll clear the second obstacle, I'm not interested in how likely it is that anybody is a man. I'm interested in how likely it is that somebody who wears a hat is a man, because I already know by the point that we've gotten in the race that they do wear a hat. We write this symbol of the chance of being a man given that you're wearing a hat with a vertical line. It's read as probability of man given hat. So let's figure this out. Probability of man given hat. The given's what you already know. So in this picture, if you ain't wearing a hat, you're not part of the discussion. Bye-bye. There are 4 people left, as you can see. And out of the 4 people who are left, 3 of them are men. So given that you're wearing a hat, the chance of being a man is 3/4. Let's see if this obstacle course approach gives us what we want, the chance of both man and hat. We're saying that to run the course, first you have to clear the hat obstacle, 50% chance of that, and then given that I know that you did that, you have to clear the man obstacle. Well, if you cleared the hat one, there's a 75% chance you're clearing the man one. And always means times, so if you multiply those together, you get 0.375, or 3/8. But is that actually right? Is that the chance of being a man and wearing a hat? Let's find out. Here are the 8 people. We'll cross out the people who aren't wearing hats and cross out the people who aren't men. What's left is men with hats. Out of the 8 people we started with, 3 of them are men with hats. Chance? 3/8. Just what our calculation gave us. So there are a few things to keep in mind about joint probability, and conditional probability too for that matter. The first one is that when you're doing joint probability, when you're doing and, order doesn't matter. The probability of shoes and socks is the same as the probability of socks and shoes. In our man with the hat example, if you first wanted to find probability of man, followed by probability of hat given man, you would have gotten the same answer. The second thing is that English has several different ways of saying and. For example, if I say a blonde woman, that's a person who is both blonde and female. Also, the word but means exactly the same thing as and when it comes to probability. I didn't study, but I passed is the same as I didn't study and I passed. It says the 2 things happened. 1, you didn't study. 2, you passed. And finally, with conditionals, order does matter. The probability of being famous, given that you're a Kardashian, is pretty high. The chance of being a Kardashian, given that you're famous, trust me, it's pretty low. So with what you know now and the obstacle course interpretation, you should be able to find the joint probability of multiple events. But you saw that sometimes to do so, you need to have a conditional probability in order to figure it out. On the other hand, in our first example, we didn't. Why is it that sometimes you do and sometimes you don't? That's the first thing we're going to be talking about in the next video. And then we'll wrap things up by finally getting back to the game of cat or no cat that we started with in the last video, and figuring out how to play the game and make a lot of money.